All right, this is our new part 2 for chapter 8 for our flipped classroom, since the Panopto video seems to have lost its marbles. So in chapter 8 up to this point, we've talked about rotation, we've talked about rolling, and we've talked about statics, where we have to have the sum of the forces in the x direction equals 0, the sum of the forces in the y equals 0, and the net torque is equal to 0. But now we're going to talk about dynamics, which means that we have things that are moving, and that means that the net torque does not equal 0, right? It could also, by the way, equal 0 if it's moving with a constant angular velocity, right? But pretty much in part 1, right? Part 1, right, we talked a lot about statics if we talked about a system. And now in this part 2, we're going to talk about dynamics, which means that we're going to, can't spell, apply the rotational form of Newton's second law. So, right, in Newton's second law, F net equals ma, where m is the mass and a is the acceleration of the system. And now we have I, which is the moment of inertia. It's analogous to mass. And then angular acceleration, alpha, which we already know, right, is related to tangential acceleration, which is going to be what we'll call the rotational acceleration of the center of mass. So this I depends on the mass and the size of the object, but it also depends on the shape. And lucky us, right, the book has already provided us this table, which this is just a subset of, where, right, for a particle means, right, an object where the shape doesn't matter. So this could be a child sitting on, right, a teeter-totter or a seesaw. It doesn't mean that it's actually a physical particle like an electron. Here we have a thin rod. If it's rotating about the center of mass, the moment of inertia is 1/12 ml squared, m the mass of the rod, L the length of the rod. If we move it to one end, then our moment of inertia is now 4 times larger. And we can use this equation, right? A disk, right? So something like a pulley, 1/2 mr squared. So the mass and r is the radius, right? A hollow cylinder and a solid sphere, 2/5 mr squared. And there's more, and the complete sheet will be actually attached to test 3 as part of our equation sheet. So moment of inertia, we could tell that it has units of kilogram meter squared. So for instance, the moment of inertia of a disk or a cylinder, right, a solid cylinder, that would be 1/2 mr squared, right? M is in kilograms, R is in meters, so kilogram meters squared. Moment of inertia does not have its own units, so that's the units of moment of inertia. If we think about it in terms of the rotational form of Newton's second law, the bigger I is, right, the smaller alpha is, if we apply the same total torque. Likewise, right, if we want to have a certain alpha, right, then we might have to apply more torque if I is, right, bigger, because the mass is twice as big or something, right? So it's that same kind of relationship where I and alpha are inversely proportional, just like M and A, right? We can find the net torque just like we did in the first part of chapter 8. It's just that now it won't be equal to 0. It'll be equal to I times alpha, right? Just like way back in chapter 4, when sometimes we had F net equal to 0 and sometimes F net equaled MA. there is a possibility, right? So we looked at our rod and we had, if it was rotating about the center of mass, my moment of inertia was 1/12 ml squared. And if it was rotating about one end, it was 4 times larger, 1/3 ml squared. But what if it's not on the end and it's not at the center of mass? Then we use this parallel axis theorem. So here is just a picture from the book, but maybe let's say that this was the rod, right? And here's the center of mass through the physical center. And it was actually rotating about an axis right here, right? And this was, I don't know, I'll make something up, like 20 centimeters from the center of mass, then D would be equal to 0.20 meters. And so I would take, right, the moment of inertia about the center of mass, whoops, that would be 1/12 ml squared. But it's going to be bigger because it's not rotating about the center of mass. So then I would add to that the mass of my rod times d squared. So in this case, 0.20 meters squared. So it'd just be larger. And that's the whole idea of the relationship between rotating about the center of mass and the moment of inertia. If it's not rotating about the center of mass, it's always larger. If it's not something that's in figure 815, like our rod, right, rotating about one end, then we have to add this factor in order to find the real moment of inertia. Moment of inertia is not a vector, so it always adds, right? And we'll do a problem in class that's much like that. So here we have, right, a simple system where I have a rod. It is supported on this beam, and then there is a string that's tied to the ceiling. So we have, right, this support upward force, right? It's kind of like a normal force. We have a tension, and then at the center of mass, we have the rod. I don't know why it's not together like that. mg. And so we look up, right, the rotating rod. We already know it's 1/12 ml squared. And so if we put those numbers in, we get 0.63 kilogram meter squared. But in our case, again, right, it's rotating 20 centimeters away from the center of mass. And so we have to add this fudge factor. So there's the mass, 8 kilograms, times how far away the axis of rotation is from the center of mass, right? 0.2 meters all squared. That means that it's going to increase by about 50%. So I went from 0.63 kilogram meter squared to 0.95 kilogram meter squared, simply by moving the axis of rotation away from the center of mass. It doesn't matter which, if it was moved 20 centimeters to the left or 20 centimeters to the right, we would still add the same amount, 0.32 kilogram meter squared. So here is our rod. We have our support. We figured out our moment of inertia. And now we need to figure out, right, some other things. So we know that the net force in the y direction is equal to 0 because it's static, it's not moving. So I have, right, the force of the support upward, I have the tension upward, and then downward I have the weight of the rod. But that's not enough to help me figure out these two unknowns. And so very much like we would have done in the first part of chapter 8, right, F net is, or torque net, is going to be equal to 0. So I have, right, the weight of the rod times D. So this is D from the axis of rotation to where the weight is applied. And then I have another distance that is from the axis of rotation to the tension. This T is not a tau, it's a different T. This is a Greek letter. No, Greek should be capitalize. So here, right, I have the weight of my rod times its perpendicular lever arm, which is D. And then, right, that's clockwise, so we'll say that's positive. The support, it goes through the axis of rotation, so no torque caused by that. And then I have my tension, which is also got, right, a perpendicular lever arm for my tension. And oops, that should be T. Yeah, T perpendicular. So that means that here, I know that these add up to 0, and so I can calculate the tension in my rod, right? Oh, look at that. It's a problem from the first part of chapter 8. But what happens if now we manage to cut the string? We cut the string in a way that doesn't introduce any additional forces, and so now our rod is free to rotate about this axis, right? We'll pretend there's a hinge there. It's not going to move any direction except rotating. Now I only have, right, a force acting at the support, and I have the weight of the rod. The weight of the rod is the only thing, right, only force acting a distance away from the axis of rotation. So my net torque is only caused by the weight of the rod, right? If it didn't have any weight, it would just float there, I guess. So we can figure out what that is, right? It's the weight times the lever arm, 16 Newton meters. Well, if I know the net force acting and it's not equal to 0, then I can say, oh, well, I know that the net torque is equal to I times alpha. I figured out what I was in a previous slide. I figured out what the torque is right here. So now I can figure out what alpha is. So I have 16 Newton meters divided by 0.95 kilogram meters squared. And that gives me 17, right? Because of my cancellation of units, meters and meters, Newton. A Newton is a kilogram meter per second squared. So that cancels out another meter, cancels out the kilograms. And so I end up with something per second squared. Alpha has to have units of radians, so radians per second squared. This is the same idea as if I did a chapter 5 kind of, or sorry, 4 problem, chapter 4 problem, but I did not have a massless pulley, right? You know, might have wondered why all of our pulleys were massless in chapter 4. It's because there's actually, the pulley actually rotates because there is a torque acting, and so I can look at it in parts, right? So that I look at the force acting on just box 1, right? And I look at the forces acting on just, right, box 2, and then I have to look at the torque acting, right? Because I have tension 1 at a distance, right? And then I have another torque caused by tension 2. Whoops, goes the other way. Right, because tensions go like this, right? And so I have torque acting on my pulley, tension 1 times the radius of my pulley, minus tension 2 times the radius of the pulley. What do I know? It equals I alpha. It's a pulley. It's rotating about its center of mass. We just assume that things rotate about the center of mass unless they tell us otherwise. So we look up in table 815, and for a pulley, a solid disc, right, the moment of inertia is 1/2 mr squared. I know that alpha is, right, related to the tangential velocity or acceleration. So back in chapter, right, 7, and hinted at it earlier in this chapter, the acceleration of my system is related to the angular acceleration of my pulley, which is rotating without slipping. And so we have R times alpha. And so we can do more here, right? And in this problem, our two tensions are not equal to each other. Tension 1 and tension 2. They're different. We can also look at other things from earlier in the semester. So we could have rotational power and rotational work and rotational kinetic energy, right? So if we are making something rotate, it can still do work because it's got a change in its angular displacement. And I can have rotational energy. So back in chapter 5, we had what was really translational or linear kinetic energy, 1/2 mv squared, right? We had power that was the rate of work over time. Notice that's the same, right? And now we have rotational work, which sometimes we can talk about in terms of the change in kinetic energy, where it's the change in rotational kinetic energy. We could also represent it as a torque, right? Making an object go through a distance, a rotational distance, where this is in Newton meters and theta has to be in radians. So a lot of the same ideas, right? Just expanded now from just linear, right, to also rotational, which is kind of what this chapter is all about. So say I have, it's phonograph record, it's a record, right? Wilson may have been very old. So we know what the radius is of the whole disc. So it's 0.15 meters. It drops onto a turntable because that's what used to happen a long time ago. And it's rotating at 33 1/3 revolutions per minute. So we'll just write that as 33.33 revolutions per minute. We want to know how much work must be supplied to get the record to rotate at this speed, right? It started off at rest, right? And what supplies the work? Well, the turntable does. So we can look at, we want to know about the work, right? Those little W's are not, right? They're not W's, they're omegas, right? So we say, oh, well, we could represent the work done really two different ways. We could look at it as far as the change in kinetic energy or the torque times the angular displacement. But here we don't know about the torque, we don't know about the angular displacement, but we do know about the angular speeds. So we know that kinetic energy, when we talk about rotational kinetic energy, is 1/2 times the moment of inertia times omega squared. Right? So exactly the same form as we had really in chapter 5, just in rotational form. So we say, oh, well, it's a record, it's a solid disk, kind of like a pulley. So the moment of inertia, right, it's rotating about its center of mass, is going to be the mass times the radius squared. Oh, well, we do know the mass, right? So we know the mass of the record is 0.0050 kilograms. And we know what omega is. So the work done is the change in kinetic energy, the final minus the initial. That means that I have 1/2 I omega squared minus 0 because it wasn't doing anything before I turned the record player on. And so now I have 1/2 times the moment of inertia, 1/2 mr squared times omega squared. So that's 1/4 mr squared omega. And now I can plug numbers in. So I have 1/4 times my mass, 0.0, oh, I got too many zeros in here, 0.50 kilograms times the radius, 0.15 meters all squared times 33. Oh, wait a minute, I got a problem. This is in revolutions per minute, and to make this turn out as work in joules, omega has to be in radians per second, not revolutions per minute. So now I have to do a conversion. So I have 33.33 revolutions per minute. Right? 1 minute has 60 seconds. 1 revolution has 2 pi radians. And so now I can figure out what omega is, right? But I can't use the value in revolutions per minute. So I have 33 1/3, right, times 2 times pi. Find pi on my calculator. There it is. Right? Divided by 60. And that gives me 3.49 radians per second. So now I'm ready to figure out the work. So open that squared. So I square that, right, times 0.15 squared times 0.05 times 1/4 or a quarter. And I get the work done is 0.0034 joules. Still joules because it's energy, right? I got kilogram meters squared per second squared. That still gives me Newton meters, but it's energy, so it's in joules. We could do something similar to what we would have also done in chapter 5, where we have an object that starts from rest at the top of a ramp, and then it rolls down so that when it's here, right, it's got some non-zero angular velocity and some non-zero velocity of the center of mass. And we could do this problem exactly like we would have in chapter 5. The difference is that now I have to worry about rotational kinetic energy. So I have to include, right, mgh initial, and I have to include the linear form of the kinetic energy, and I have to include the rotational form of my kinetic energy. And then that has to equal, right, mgh, which here, right, this is where it gets to the ground. There's no. And then my linear, because I'm rolling, so I have linear kinetic energy and I have rotational kinetic energy. And I can relate omega and v. Right? If I make it r, like a capital R, right, that would be just r omega. So I can do some substituting. It's a solid sphere, so I can look up in the table, and that's 2/5 mr squared. It's rotating about its center of mass, right, because it's a uniform sphere. It's just rolling on its own, and that means it's rotating about its center of mass. So at the top of the incline, right, we have no kinetic or potential energy, or sorry, we have no linear kinetic energy or rotational kinetic energy. All we have is potential energy. At the bottom of the incline, we have no potential energy left. All of the potential energy we started off with has been converted to kinetic energy. Just like if we had a box going down our incline, except that we have to worry about the shape of the object because it's rolling. Right? We're not worried about friction. There's just enough friction to make my object roll, but not enough friction to mess up my conservation of mechanical energy. So there's my moment of inertia of my sphere. 2/5 mr squared, right? I'm going to get rid of my omega by just taking my v is equal to r omega and just setting it up so I can replace omega. Because in this particular problem, they told me about the velocity. Oh, sorry, we want to find the velocity. So now I can just combine these things, right? This cancels this. I have a half plus a fifth. That's 7/10. You know, like denominators and stuff. So it ends up that the mass of my sphere doesn't even matter when it comes to the velocity of the sphere at the bottom. What matters is the shape. So my m's cancel. I solve for v. That's the velocity of the center of mass. And I get 2.5 meters per second. If I change the object to a cylinder, now I go from 2/5 mr squared to 1/2 mr squared. Slightly changing the shape slightly changes the velocity at the bottom of the incline. If it was a box, right, so it was just sliding down, then it would go faster, 3 meters per second, because I'm not converting any of my initial potential energy into rotational kinetic energy. So it takes energy to make an object rotate as well as for it to move linearly. We can also look at this in terms of forces acting, if that's what we're interested in. So we can apply Newton's second law. In this case, we have the two components of the weight and the normal force. The edge doesn't belong there. These all act through the center of mass. So these three that are underlined cannot cause torque. So all of these, right, cause a zero torque because they act through the center of mass, so they don't have a lever arm. So all of the lever arms, right, perpendicular lever arm is 0. If we set it up, right, like we would have in, right, chapter 4, we have friction acting, we have mg sine of theta acting in the line of motion. But notice that the force of static friction maximum is acting at the surface, right? And so it actually does cause a torque. That's why the object rotates, okay, while it's rolling down. So here, right, I have actually two unknowns, right? I would have A and the force of static friction maximum. If I don't know anything about the coefficient of friction, I can still figure out a relationship for the force of static friction maximum based on the torque. Net torque equals I alpha. And so it's a sphere. I substitute in again 2/5 mr squared. It's a uniform sphere rotating about its center of mass. And then it's rolling without slipping. So tangential acceleration is r times alpha. But now this is the acceleration of the center of mass. Remember, that's the connection between what we learned in 7 and what we know in 8. So now I know the torque is the force of static friction maximum times the radius of my sphere. And that in turn equals I times alpha. So I'm going to substitute in here A divided by R. And if I do that, I end up with a very interesting situation where I end up with a value for the force of static friction maximum that is based on the shape. That's where the 2/5 comes from, because it was a sphere, and the mass times the acceleration. So it ends up that, right, my radii cancel, And so my force is based on the shape and the mass and the acceleration of my system, but not on, right, the size of it. And now I can have two equations and two unknowns, and I can do some substitutions, and I end up that the acceleration of the center of mass is 3.5 meters per second squared. I could show this maybe by flashing back to chapter 2 and figuring out the same thing, and I end up with, right, A is 3.5 meters per second squared. But in that case, right, I need to know what the final velocity is. But we know that because we found the final velocity for a sphere rolling down by using conservation of energy. So a little more complicated than just a chapter 2 problem. If I change the object from a sphere to a cylinder, then I go from 5/7 g sine of theta to 3/2, right? Because I changed the shape. And that in turn changes the acceleration of my system. I could verify that also by looking at applying kinematic equation, because I know that for a cylinder at the bottom of the incline, using conservation of energy for rolling, I have a velocity of the center of mass of 2.4 meters per second. So I can again verify, right, the same thing. So we can see that there are a lot of connections between what we learned in chapters 2 through 6 and what we are doing now in chapter 8. So torque is just the rotational version of force. Moment of inertia is like the rotational form of mass. Newton's second law also has a rotational form. We can still do work with rotation, power with rotation. We can have, right, rotational kinetic energy, or we can combine it with linear, right, if our object is rotating and also moving linearly down an incline. And it ends up that we also have angular momentum. It's analogous to linear momentum is mass times velocity. Now for angular momentum, it's based on the shape, which is I, which also includes, right, the mass and the radius, times omega, which is going to be the angular velocity. So if we do that, right, we can see that just like the net force was acting on an object after a collision was the change in momentum over time, now the net torque is the change in angular momentum over time. Angular momentum again is I times omega, right? Where L and omega are in the same direction, just like P, the linear momentum, right, for object 1 was object 1's mass times its velocity, right? If the velocity was to the right, then the linear momentum was to the right. Ends up exactly with the same units as linear momentum, kilogram meters squared per second, which is the same as a Newton second. And just like linear momentum, it can be conserved. We just don't have to worry about components because we have only two types of direction, right? Clockwise and counterclockwise. So these, right, have direction or angular speed. So they're either clockwise or counterclockwise. Moment of inertia is more like mass. And so if we have maybe a skater has their arms outstretched, they have a larger moment of inertia, they bring their arms in, their moment of inertia decreases, and then they spin faster. And here we can look at that same idea by putting some numbers to it. So say that our ice skater spins at 2 radians per second with her arms outstretched. She brings her arms in. Her angular speed doubles. And we are told that when her arms are out, her moment of inertia is 8 kilogram meters squared. And we want to know what is her moment of inertia when she brings her arms in. Well, we could show that using equations, which, we'd have to do maybe on a test. But we might be able to look at it and say, well, 8 times 2 is 16, right? And then my speed doubles. So if this doubles, right, then this has to be half in order to get the same numbers on the left side and right side of our equal sign. But we can show it mathematically, doing a little algebra. Oh, look at that. It ends up exactly like we would have thought, just kind of through a thought experiment. But of course, on tests, we always want to show the original equation and any work that we used in order to demonstrate our answer. So a summary of chapter 8, right, up through chapters 2 through 6, we had only linear motion. In 7, we had only rotational motion. And now we bring it all together and we can have rolling without slipping, right? And we can have torque, and we can have mechanical equilibrium, which just means that we have statics where the sum of the forces in, right, multiple directions equals 0, and the sum of the torques equals 0. Or, right, we can have the net torque equal to some number, which then in turn is equal to I times alpha. We can calculate I, not usually as the sum of m times r squared, but by looking at our chart figure 815, right? If it's not rotating about its center of mass, which will not be true, right? If it's rolling, it's always going to be rotating about its center of mass. And then we can have rotational work and power and kinetic energy, right? Again, treated very much like what we did back in earlier chapters, right? These are all scalars, which means that they are not vectors, so they don't have direction. Right? This is also a scalar, just like mass is a scalar. Torque is a vector. But we only have 2 kinds of direction, right? Clockwise and counterclockwise. And then finally, we can think about momentum in terms of rotation, so that we have angular momentum. It looks like an L, but it's angular. It's actually a capital lambda, right? Lambda means it's angular momentum. And then we can relate, right, our change in angular momentum with the torque acting, very much like we did when we talked about collisions. Here we can have a collision in a different way, like our skater pulling her arms in, but also other ways, such as, right, having a cog that's rotating and then it runs into another cog, and then, right, their momentum, angular momentum, remains the same. We just have more mass. And we'll do some things like that in class. And that's it.